Hi, good morning, everybody. Glad you're all here again today. Hope you enjoyed your weekend. We have a week. 1 week. And I believe it was Xavier. He was not in this class, but I thought it was a good idea. He's like, can we go over some of that stuff from Unit 8, the chi-squared stuff? I was like, we can do that. So just in case that stuff slipped your mind, I'm going to try and distill the important bits of that unit today. Starting with this, I think this is the best overview that I could possibly give you. So if you're working with chi-squared data, if you're doing a chi-squared test, which by the way is when you have categorical variables, it's the only type of test we've looked at all year where we have categorical data. So if you ever have one of those multiple choice questions, it's like, which is appropriate? And it's got chi-squared and like a z-test and t-test and stuff. If the data are categorical, it's gotta be chi-squared. Okay. There are 3 different tests: the goodness of fit test, homogeneity, and independence. And which one is appropriate depends on both the data that you have and the question that's being asked. If there's only one variable given to you, it has to be a goodness of fit test. That's the only one of the 3 where there's only one data set. And it'll ask something like, do sample proportions, I should have written sample proportions there, fit an existing distribution? So that'll be where it says something like, oh, we think that the distribution of rainy days during the week is it rains 15% of the time on Monday, 20% of the time on Tuesday, so on and so forth. We took a sample from like a whole year, and this is the proportion, or this is the count of days of each day of the week that it rained. Does our sample match the distribution that we thought it did? Goodness of fit test. And if you have to do that on your calculator, it's the chi-squared Goff test. These 2 are the 2 that usually get confused, homogeneity and independence. And it's because for both of them, there are 2 categorical variables, and usually they're presented in a 2-way table. So the way it's presented is very similar looking. But sometimes the variables come from different populations, and other times they're from the same population. That should be clear from the information you're given in the problem, whether it's 2 populations or 1. And just in case that's not clear, the question that they're asking makes it very obvious which test it should be. For the test of homogeneity, it will ask, are the distributions the same? Are they homogeneous? Whereas for the independence test, it will ask, are the variables associated, or are they independent? Okay. So, probably the best single thing that you can try and do to be prepared for the test is to know, given the data and the question, which test is appropriate from these 3. With that in mind, I do have some problems for us to work through. They are on AP Classroom, so if you want to bring them up as we talk about them, maybe that would help. But we'll go ahead and do that. My clicker's over here. I know the type can be a little small and difficult to read, which is why I suggest you might want to do it on your own Chromebooks also. All right, anyway, so this is, if you go to AP Classroom, it's called chi-square review. So, you're taking the AP test a week from today. You're just starting the free response questions section, and this is the first one that you see. We'll walk through it together. That way you'll have at least a plan of attack. Right. So we have a table here. This is a 2-way table. It's not going to be this. Right. And a bar chart summarizing the age of diagnosis in years from a random sample of 207 men and women currently being treated for something. I no longer can read. Schizophrenia. Perfect. Okay. So we've got the counts there. We've got this segmented bar chart here, okay? It's a very simple question. It doesn't even have parts A, B, C, whatever. Do the data provide convincing statistical evidence of an association between age group and gender in the diagnosis of schizophrenia? kind of given the game away a little bit. This is going to be a chi-squared test. If you didn't know that, how could you figure that out from this?
The variables are categorical.
Yeah, the variables are categorical. We have gender and age group. Not age, but age group. Anytime you see data in a two-way table, it's going to be categorical data and it's going to be a chi-squared test. That's just the way it is. Usually I hate oversimplifying things like that, but it's true here. It has to be a chi-squared test. The question is, which one? We've already crossed out this one.
The independent.
Do we have a vote for independence? Agreed? Yes? Why?
Because it says, do they have an association between the age group and gender?
Perfect. Is there evidence of an association? That's exactly what a test of independence is asking. But even if it didn't ask that, or it asked something in weird wording, these variables are from the same population. They only took a single sample. And we got gender from them and which age group they're in. For it to be the test of homogeneity, they would have to be from different populations, those two variables. So, definitely a test of independence here. Question is, what do we need to put to get credit for this problem? Well, any hypothesis test, what's the first step? Even before that. I like where you're at, though. State the hypotheses. So what are the hypotheses?
The null would be that they're not associated.
Okay. No association between whatever the two variables are, age group and gender. Now, I might even suggest doing the alternative first, before the null, because that's what you're trying to prove. That's usually what the question's asking. So this is asking, is there evidence of an association between age group and gender? That's what we're trying to prove. I might have actually written the alternative first and then gotten the null from taking the opposite. But if you like doing the null first, that's the boring one, that there's no association between them. But the alternative would be that there is. I know that I always split these hypothesis tests into a 5-step process. Remember that middle step, the transition step, is stating what test you're doing. That doesn't need to be a formal step in the middle. I would go ahead and say that right here. We know this is a chi-squared test of independence. It doesn't have to be in a complete sentence. You just have to put it somewhere on the page. Step 1. On the rubric for grading this test, we have not calculated anything. But step 1 is to state the correct pair of hypotheses. So you can write it in words, like we have here. You could write it in terms of symbols, but I really wouldn't recommend it. So the null hypothesis is that age group and gender are independent, or that there's no association. And the alternative is that there is an association, or that they're not independent. Okay. Step 1, that gets graded all by itself. You get an E if you state both hypotheses correctly with context in at least one of them. Context being the variable names, age group and gender. You couldn't just say no association and association. And identifies a chi-squared test of independence by name or formula. By writing just that, you've started off with an E. And that's good. That's good stuff. So, we have our hypotheses. What's next? We check the relevant conditions, which are randomization. Let's go ahead and check it. Do we meet this condition?
Yes.
Random sample of 207 men and women currently being treated for schizophrenia. I might include that entire. Another condition.
Expected count.
Expected counts. That's the tough one to check, so I actually want the other one. 10% condition. We will check this, just last. Do we meet the 10% condition here? We don't know for sure, but how could we say it if it is met?
207 people, or less than 10% of people with schizophrenia.
So our sample size is less than 10% of the population, which in this case is people currently being treated for schizophrenia. And technically we're assuming that. We don't know that for sure, but it seems reasonable. Now for the expected counts, what is the condition that needs to be met before we actually do it?
At least 5 for all the cells.
Okay, there needs to be at least 5 expected in every cell. Notice this number is 3. This does not mean the condition fails. These aren't the expected counts. These are the ones we actually observed in our sample. To get the expected counts, does anyone remember how to do that?
Isn't it where you take the percentage, like, from, I don't know how to word it.
No, we just kind of plug it in the calculator.
We use the calculator?
Yeah,
What do we do?
never mind. I know we put it in the matrix, but
Right. If you don't remember, you know that this is going to be using chi-squared test on your calculator. If you go to that, it will say observed A, expected B. You have to enter the data from this two-way table into matrix A on your calculator. So, remember you're only putting in the observed counts, not the totals. So you're gonna need a 2x4 matrix. Go ahead and plug those observed counts into matrix A, and go ahead and do the test on your calculator.
where do I find the chi-squared test on the calculator?
Same place as all the other tests. That's going to be stat, and then tests. You see it?
Mhm.
Okay. When you do the test, that's the only way to get the expected counts matrix. It actually gives you the results of the test. I'm going to just write that off to the side, because that's probably going to be important. Gives us our test statistic, p-value, degrees of freedom. Do those match? Did you get those as well? Yeah, okay. And then just go back to second matrix and pretend like you're editing matrix B to view those values.
Do you have to type every single expected count?
Well, first of all, the test is going to be paper pencil. So, no, you will have to write them all though. You do have to check the condition is met. You can't just say all expected counts are greater than 5. You have to show what they are. And maybe I put a little bit more detail into this than I need, but I want to make sure that I label them correctly. So I'm going to remake this two-way table with the categories and then put the expected values where they go. It takes a little bit of time, but again, this is something that you will know how to do, and you should make sure you get full credit for it. If you just list the expected counts without labeling where they belong, you might get dinged for that. Same expected counts you ended up with? Okay. How about even do that? Okay, so since all expected counts are greater than 5, the condition is met. Okay. We still haven't done the test yet. We haven't reported anything. We have those values, but we haven't used them yet. But I think this was step 2. Okay, we already identified the correct test procedure by name. So the conditions, it says the sample is randomly selected. We check that one. The expected counts are here. And again, that's what we have. This is computer output. They don't expect you to actually write all that. Okay, so step 2 is essentially just checking conditions. For this section, you get an E if you, really? Oh, this is all still section 1, verifying the appropriate conditions. Okay. They have to include at least the condition for expected counts and not include any incorrect ones. So again, this is from an older test. You would have to explain all 3 of these now. Okay. My bad, that's all section 1. But now that we know all the conditions are met, we can actually do the test. Okay. So we're all the way down to calculating the test statistic. We know it's 10.88. But just to be safe, does anyone have a formula sheet on them? I don't know if the formula for the chi-squared test statistic is on there. I think it is, because it's different from the rest.
Yeah, it's the added all of the observed minus expected squared over the expected.
It says this? Perfect. If you write this formula, and then write that it's equal to 10.88, you're good. If you only write that it's equal to 10.88, they might ding you for not knowing what the formula is, but it's on the formula sheet. Report your p-value and degrees of freedom also. Everything that the calculator gave you when you did the test. My guess is this is section 2. Okay, we have the right p-value. If you were to do all of that arithmetic, you would get 10.884. P-value is 0.012. And there are 3 degrees of freedom, which again, you could use the formula, but you don't have to show it. So you get another E as long as you provide the right chi-squared test statistic value. We got that from the calculator. And the right p-value. Okay, we're not messing with this other stuff. We're just reporting the correct p-value. Okay. According to this, you didn't have to write the formula for chi-squared test statistic. Do it anyway. You don't want to give them any reason to ding you. Right? So for what we've done so far, the hypotheses, test name, and conditions give you an E. The correct test statistic and p-value give you an E. I've also seen in the past where you had to cite the degrees of freedom to get an E. So I'll go ahead and do that as well. Okay. So we haven't actually answered the question yet. Do we have convincing statistical evidence of an association between these variables?
Yes.
We do? Why?
P-value is less than 0.05.
This is where we compare the p-value to alpha, which they didn't give us, so we'll just assume it's 0.05. So go ahead and write out your comparison of p-value to alpha. This is the most important part of this entire thing that you're writing. If you don't write that, you won't get an E for this. What do we do with the null hypothesis?
Reject.
We reject because the p-value is less than alpha. And if we reject the null hypothesis, what you write here can either be copied from the question or from your alternative hypothesis. Okay, we have evidence of this association. Okay. This was from 2017. Interesting. Okay, so for the last section, you get an E if you make a correct conclusion about the alternative hypothesis. Essentially, that you're saying that there's evidence of it. Justification of the conclusion based on the linkage between the p-value and a reasonable alpha. That's this. And the conclusion is stated in context. You've got variable names there. Okay, that's all you need for an E. If you wrote just this, you're going to get full credit on this problem. You'll get a 4. So my hope is that even if you didn't know what to do at every single step, that it does make sense. There is a logical pattern. For any hypothesis test you need to do, hypotheses, name of your test, conditions, do the test on your calculator if you can, report all the relevant stuff, conclusion. Even if you miss a piece or two, you can still get a P. That's something. It's not an I. P's are good enough. Okay. Any questions about this test in particular? Okay. Number 2 is another free response question. We're not going to go all the way through it, but I wanted to show you what it might look like if it were a chi-squared goodness of fit test problem. Okay. So you've got all this detail in question 2. We're talking about moose. And these moose are found in a region containing a large burned area. You've got 4 different areas here. Okay. And it has a proportion of the total acreage versus the number of moose observed in each of these areas. And essentially the question they're asking is, from the sample of moose that we observed in each area, does it match the proportion based on the acreage alone? Classic goodness of fit problem. Because you're comparing your sample counts to a distribution, essentially. Okay. Yeah, I think, yeah. So this one's even easier. It says conduct an appropriate statistical test to support your conclusion of this. Assume the conditions are met. Score. The whole conditions part, all you have to say is, the problem says the conditions are met. Boom, you can move on. Okay. So as long as you had your hypotheses, you named the goodness of fit test, and then did the test on your calculator, reported those and concluded, you can get an E. As long as you knew what you were doing. Okay. But I want to also go through some multiple choice questions related to this unit. Oopsies. You didn't see that. In this question, there are several things that tip you off to the fact that this is a chi-squared test. What up?
Categorical.
Where?
The age groups,
That's one of the variables. What's the other one?
and then the major brands and cell phones.
Cell phone brands. Age groups and cell phone brands. Those are both categorical variables. So this would have to be chi-squared. Anything else? Okay, references a contingency table, which is another name for a two-way table. So even if you miss the fact that they were categorical variables, it's telling you there's a two-way table involved. How do you choose between those two? Whether there's an association. So it has to be
In
test of independence. Okay. These are the types of things that I want you to be looking for on questions like these, where you're determining which one is appropriate. I think it's actually easier to look for wrong answers to get rid of first than it is to look for the right answer. It actually might be the case for most multiple choice questions, but these in particular. Next. There are two ways I can think of to get the answer for this. There's an easy, fast way, and there's a still easy but not so fast way. The fast way involves you knowing how the expected counts are calculated from a two-way table. Does anybody know? It is row total times column total divided by total total, grand total. So if we're looking at age 30 to 50, that's this row, and preferred green, that's this column, we're going to take 108 times 99 and divide by 314. That's going to be A, I believe. Yes, that's the fast way. If you did not know that, how could you still get the answer? Put them in the calculator like you just did. You'll get the table of expected counts in your matrix, and you can calculate all of these and see which one matches it. You can still do it that way. It will take you longer, because you will have to type all of these in your calculator. I think the reason they made such a big table, they're trying to discourage you from doing that. And that's also why they wrote the answers this way instead of as whole numbers or decimals. Okay. But there are multiple ways to attack it. All right, here. Context is important, but if you're running low on time, I'm getting a little discouraged by seeing all these words. My guess is most of them don't matter. I'm skipping right to what it's asking. Which is closest to the p-value of the appropriate test? I ain't read any of this. I need to find the p-value from this. I don't need to know the context of the problem. I don't need to read any of this. I don't know if I should be telling you that, because it could get you in trouble. But if you've got a two-way table here and you need to find the p-value, you're doing chi-square test on your calculator, for sure. Put these values into matrix A, push chi-squared test, and within about 20 seconds, you should get the p-value. As long as you know what it is you need to do, doing it should be very easy. Okay. So one of the things I'm trying to really push onto you today, two-way table, chi-squared test, one of these two. It doesn't even matter which one it is. Okay? See if you can save yourself some time. Those are the only parts of the question that are important. That's all you need to answer it. P-value and alpha. Is the p-value bigger than alpha or less than alpha?
Bigger?
It's bigger than alpha. So is there evidence of something or not?
No.
No. So you're down to 3. They love throwing prove versus suggest here. We don't prove things in statistics. That's what calculus is for. Right? We don't prove anything with a sample, ever. So that has to be wrong. So there's not convincing statistical evidence to suggest is the same or not the same. Which one of those sounds like the alternative hypothesis?
The same.
So you might, on your scratch paper, just quickly maybe write what the hypotheses might be. So this is where I might actually go back up into the question. Okay, so this is a goodness of fit test, right? Because there's only one sample. So for a chi-square goodness of fit test, the null hypothesis is that the proportions are the same. And the alternative is that they're different. Remember, the alternative is what we're trying to prove. We're trying to show that their satisfaction changes, or sorry, their classification changes based on whether they order dessert or not. So the alternative would actually be that they're not the same proportions. And even if you got it down to those two, it's not the worst thing in the world. It's at least 50-50. Right? Which of the following is true about the chi-square test for homogeneity? Well, some of these are easier to check than others. This says not all of the observed cell counts are large enough to satisfy the conditions. Conditions have nothing to do with observed counts. This one says the expected counts aren't large enough, but they're all bigger than 5. It says volunteers were randomly assigned, so independence has been met. Were they randomly assigned to each treatment? Yes, randomly assigned to the treatments. So that looks good. Is that the answer here? I think it is. Yeah, that's correct. For an experiment, all you need is random assignment of treatments. That means these two are wrong. The number of subjects is not the same, so it's not appropriate to do the test. That's just nonsense. They don't need to be the same. Volunteers don't constitute a random sample, so it's not appropriate. Again, this is an experiment, which you may have gone into the problem to know, okay? But you're allowed to have volunteers. It's the random assignment of treatments that's important for randomization. Okay. Last thing, interpreting a p-value. There's nothing chi-squared about this. The way you interpret a p-value is the same no matter what the test is. You always assume that the null is true. So you would have had to know what the null is for this. For the chi-square test of homogeneity, it's that the proportions are the same in both populations. So assuming that each high school has the same absentee rate, these are going to be wrong. There's a 2.5% chance of finding a test statistic that were smaller or that were larger. Do you remember when we sketched the chi-square distribution where we shade?
Right.
It's always to the right. So it would always be that or larger. And again, I would hope that you could at least get that down to these 3, preferably even these 2. And then if you had to guess, fine, but at least try and reduce the possible choices by looking for ones that are wrong. All right. Thanks, guys. Tomorrow, I think I'll ask you what you want to do for review, because I've got several things that we could do. I want to do whatever helps you the most.